Hello and welcome back to College Algebra. In this video we're going to talk about piecewise functions. Piecewise functions are any function that behaves like different functions depending upon which part or piece of the domain it's in. In every definition of a piecewise function, you're going to see little statements about where you use certain formulas to graph the function or to find function values. So we're going to look at some examples from the book. This is from section 3.4. It's from Sullivan's College Algebra 10th edition, Pearson's 2016 book. This is section 3.4, problem 37. It's on page 245 in the book. And we are going to graph the function. We're going to find the domain, and we're going to answer the question, is the function continuous? O-U-S. Oh, I need an extra U. U. Continuous. There we go. On its domain. So let's see here. Here is the function. F of x equals. Here's the first piecewise function you've probably seen. It is 1 plus x. I guess we've seen the absolute value before this. If x is less than 0, and it is x squared if x is greater than or equal 0. So this is the formula. This is the condition. So these are the pieces of the domain over here, the conditions are. So for x values less than 0, we're using this formula, which is a line. For x values greater than or equal 0, we're using this formula. So y equals 1 plus x. For any x values less than 0, y equals x squared. For any x values greater than or equal 0. So let's go ahead and make ourselves some axes to draw on. Alright, make ourselves a point table, so you can see where we're doing. Let's do the first part, the y equal 1 plus x. So that's only going to be for x values less than 0. So I do actually want to plug in 0, even though I don't actually have a point there. But at 0, it should be approximately, because it goes up to but doesn't include it. Don't need to say anything about that. I'll just erase that. There we go. At 0, it should be approximately, let's see, 1 plus 0 is 1. Now let's pick values less than 0. So negative 1, 0, negative 2, negative 1. That should be plenty. I didn't draw my horizontal axis. I'm just using these guidelines that are already there, so. Alright, so let's see here. 0, 1. Now, it's important here, we don't have a point there. Here, so instead of doing a point, I'm going to do an empty circle. That means it goes up to this point but does not include it. Then at negative 1, it's 0. So right there, that's a full point. And at negative 2, it's negative 1. Alright, so we're looking at this. That's good enough. So there we go. That's the left piece of this graph. Now there's two pieces of it, so we need to make sure to include both. So x squared, that's if x is greater than or equal 0. So now we'll look at that part. Y equals x squared. Well, at 0, because we definitely want to include all the endpoints, This one actually does have a point. It says x greater than or equals 0. So 0 squared is 0. You plug in 1. 1 squared is 1. You plug in 2. 2 squared is 4. That's probably all I've got on my graph. I'll go ahead and put in the 3. I might as well. 3 squared is 9. So 0, 0. I do have a full point on this one, because the condition allowed x to be 0. 1, 1. 2, 4. And 3 would actually be up here, because this would be 9 using my scale. So let's see. There we go. This is the graph of the function. Notice it looks very different on different pieces of its domain. This part is a quadratic or a parabola. This part's a line. That's what piecewise functions do. They flip around, they behave differently. But answering the other questions, domain, well, this has values going infinitely to the left. It actually does have a point at 0 because of this point, and it goes infinitely to the right. So its domain is negative infinity to infinity. How about its range? They didn't ask for that, but we can go ahead and do that as well. Infinitely down, infinitely up, and it doesn't skip anything. It actually covers this area twice, this length twice, because it does it over here and here. So it actually has every y value as well. Is the function continuous on its domain? So a continuous function doesn't have any holes or breaks. This very clearly has a break from here to here, so this is not continuous. So there we go. That's all of that problem. Let's continue on. This is problem 44. Note we have a piecewise function given. We want to write a definition for the function. Well, you notice here we've got two segments. This tilted line and then this constant line. So the first one's really easy. They don't actually tell us what to call it. I'm going to call it H. No reason. Just wanted to call it H. Equals. The constant part, well, that is at 1. So it equals 1. And for if x is, let's see, it's between 0 and 2. So 0, x, and 2. It does have a point at 2, so less than or equal. It does not have a point at 0, so greater than. That includes this part. Now this part, that's a tilted line. It has a slope of, goes up 1 over 1, so a slope of 1. So 1x plus b, its intercept is 0, so plus 0 is just 0, so it's just x. If, and that goes between negative 1 and 0, and that has a point at both edges, so less than or equal, less than or equal. And there you go. The formula of that. We got this point by knowing y equals mx plus b. We could find the slope by noting it goes up 1 over 1, so 1 over 1. We found its intercept because it's just right here, 0. This is a horizontal line. Those are always just y equals whatever the y value is, which in this case was 1, so y equals 1. If 0 is less than x is less than or equal to. There we go. So this is exercise 58 on page 246. So this says we have holders of credit cards issued by banks, department stores, oil companies, and so on receive bills each month. They state minimum amounts that must be paid by a certain due date. Sure, I get one myself. The minimum due depends on the total amount owed. I'm not sure if that's the same for every credit card. It seems like a lot of the credit cards I've had over the years had minimum payments that were pretty standard. But maybe it increases if you just have a really big bill. One such credit card company uses the following rules. For a bill of less than $10, the entire amount is due. All right. For a bill of at least $10 but less than $500, the minimum due is $10. Minimum of $30 is due on a bill of at least $500 but less than $1,000. Minimum of $50 is due on a bill of at least $1,000 but less than $1,500. And a minimum of $70 is due on bills of $1,500 or more. Find a function that describes the minimum payment due on a bill of X dollars. Okay. F of X equals... Alright, let's just start with our first X value. So, if a bill of less than $10. So, if X is less than 10, then we're paying the entire bill. So, we're just paying X. For a bill of at least 10, so between 10 and we're including it, but less than 500. Less than 500. Oh, run out of space there. I'll redo that. So 10 less than or equal X less than 500. Then we're paying $10. Okay, $10. Then paying $30 for the next rung. And that's for 500 less than or equal to X. Less than or equal, no, less than 1,000. Then we're going up to $50. That's for 1,000. That's less than, not less than or equal. 1,000 less than or equal X. Less than 1,500. Then for everything above 1,500, we have the same thing, so we're paying 70. Another rung here. 70 if X is greater than or equal to 1,500. So there's the function. As far as graphing it, let's see here. X is, how do I want to go on my X value? I've got to get up to X equal 1,500, so I think I got to go by 100s. So that would be out to here. How about by 10s? Yeah, that'll work. So I almost want to go a little bit further just so I can get the actual 10 in, but because, you know, the X less than 10, that only goes to about right here, and it's just the identity function. X less than 10, and then it would actually go up to 10. So it would actually be like this. Go up to 10. Pretty steep. So we are 10 from 10 to 500. And that part is connected, but this next one we're actually going to have a jump. So we have an empty circle there. Then from 500 to 1,000, full circle here. We're at 30. Empty circle there. Then we jump up to 50. From 1,000 to 1,500. Empty circle there. And then we're at 70, so that's 50, 60, 70. From there on. So that would be the graph, such as it is. Alright, that'll be it for this section and for this video. Next time we'll be looking at transformations of functions. Now that we have a bunch of basic functions, including some piecewise functions, we'll look at what making a small change to the formulas does to their graphs. That'll probably be 1 or 2 videos. It's not a super long topic, but usually when I do it in class, it does take a full class session. So we'll deal with that next time. See you then.